Hi, we're Team 21004, and we created the Lightning Protection Garment Mannequin. I'll go ahead and let everyone introduce themselves.
Hi Manny, my name is Sabrina Amada and I'm the systems engineer.
Hey Manny, I'm Cameron. Nice to meet you. I'm the engineering management major.
Hi Manny, I'm Katie Daly. I'm the electrical and computer engineering major.
Hi Manny, my name is Senhadi. I'm industrial engineer. Nice to meet you.
Hi Manny, I'm Christian. Nice to meet you. I'm the mechanic engineer for this project.
Hi Manny, I'm Cassidy. I'm the biomedical engineer that's going to be working with you on this project.
Our challenge was to create a mannequin that can be used to test Zoltar's lightning protection garments. The mannequin should emulate human electrical properties while also measuring current, temperature, and voltage through the heart.
All right, Manny, now we're going to talk about how we will set you up to accurately simulate the human body. First and foremost, we need human skin. This is important because it's the body's major electrical resistance barrier. Any other fluids or tissues are pretty much irrelevant. You can fit into the range of 1,000 to 100,000 ohms, so we do have some leeway. We just simply need the skin to cover you from head to toe, providing a direct path from head to ground, and also a direct path in series to the heart, just like the human body. Well, don't worry, Manny, we didn't forget about your heart. The heart is also incredibly important when testing electrical safety because most deaths caused by lightning are actually due to cardiac arrest. Even 0.5 amps can actually cause cardiac arrest and lead to death. Your heart must be installed inside your chest, obviously, and easily integrated with the monitoring system, so we can directly measure how much current is still passing to a human heart with the garments on, and if they work. We also need your heart to be easily integrated with the skin. Now presenting your skin. We chose a electrical semiconducting tape. The volume resistivity is 1,000 ohms per centimeter. And so when covered head to toe, you will have a total resistance of 40,000 ohms. And then actually the strips inside your chest connecting to your heart are 80,000 ohms. We added a little resistance padding directly connected to the heart because we wanted to ensure that our system didn't fry and prevent too much current passing through to our own measuring system. And presenting your heart, we went with a more simple approach for the heart with a ceramic resistor. Can easily be installed with zip ties, and we can simply connect the skin or the electrical tape around either side of the heart. The current transformer can also just sit on top of the rod, and so it easily integrates with our system.
Hey Manny, I need to talk to you about the modifications and the sub-assemblies of this project. These modifications are needed in order to test the garments properly. We consider 3 sub-assemblies. The first one being you as the mannequin. The second one is the 3D box, which meant to protect the equipment from getting struck directly during testing. And lastly is the stand, which will support you during testing. In the first assembly, you as the mannequin needs to be free of metal. Therefore, the first modification needed to be done was to replace the metal joints with the 3D printed joints. These will leave your body free of any conductive metal. Also, this will give us an accurate data on our testing of the garments. At the same time, as our biomedical engineer stated, we're adding the semiconductor tape as your new skin. And lastly, it is necessary to cut a hole in your back in order to connect your new heart with our equipment. Our second assembly is the 3D box. This 3D box consists of 2 insulated boxes and a metal box, mainly made from aluminum and galvanized mesh. The insulated boxes separates the data acquisition from the battery and the computer. And lastly, you can see the 3D box is connected to the ground outlet to keep the equipment away from getting struck during testing. And our last assembly is your own stand. This stand is made of PVC tubes because of the following reasons. This design is easy to assemble and disassemble. It is also known to be not conductive as a metal stand and also not flammable as a wooden stand. And at last, it will give us a greater support in the ground in order to resist the impulse on testing.
Hi, my name's Katie Daly, and I'm the electrical and computer engineer for this project. Here's our wiring diagram. You can see that everything is powered by a 12-volt battery, which is also connected to a switch, a power switch. So from this battery, we have 2 DC to DC converters, which supplies 5.1 volts to the Raspberry Pi and 9 volts to the USB 2020 DAC. Also connected to the Raspberry Pi is a switch that initiates sampling, and this switch has a 1 kilo-ohm resistor attached and is connected to the pins of the Raspberry Pi. Also connected to the pins is an LED strip, which is used to indicate the status of the system. You also see that we have a separate DAC connected to the thermocouple, which will read temperature data from the ceramic heart rod. And the USB 2020 DAC is also connected to a USB port of the Raspberry Pi, where it acts as an onboard computer and collects all the data and displays our user interface. Connected to a channel of the USB 2020 are probes which measure the voltage across the ceramic rod. So here's our test setup. You can see that connected to the Raspberry Pi is an HDMI connection to a computer monitor to display the user interface. And you also need a computer mouse, keyboard, and USB drive in order to modify the parameters and file name that you want to save per sampling session. So this is our test setup. You can see that the wires are all connected to the battery. A little messy, but you can see that the LED strip has 5 LEDs on, and the countdown on our user interface is synced up with it, and also displays the number 5. This is our user interface. There's a lot of functionalities, including the countdown seconds, which allows you to set however many seconds you want to wait until sampling starts. So when you press the start button, it'll count down and eventually start when it gets to 0. You have options of where you want to save your file and what you want to name it. A date and time will also be added to the end of that file name. You can also adjust the samples you want to take per second and the total number of samples, and you're able to enter a description into the CSV file, just maybe of your test setup or any other notes you want to include. And then you have a split existing file option, so if you want to analyze the data in a program like Excel that has limited capacity, you can split the file into however many different files with a number of rows that you want. And then you have the status bar, which basically just updates you on the status of your sampling. So it'll tell you when you started, when it's in the process, and it will print out a status every 1 million rows it's written to the file, and then eventually tell you when it's done.
Hello everyone, my name is Hadi. I'm talking about Cube interface. Actually, we use 2 codes, first Python, second MATLAB. For Python, when we get data from DAC, then we get original CSV file. So Python will splitting the original CSV file into separate files of 1 MB. Then this code will let a user choose any number of points they want. Then they will get a new data with a new save with a new file. Second, we use the MATLAB code to analyze and plot the data. MATLAB, it's easier and it's work with a million of data points, and it's better than a Python because a Python wasn't work with a million points. Finally, the MATLAB code it's to plot the data, current, voltage, and temperature.
In conclusion, our final deliverables to our sponsor will be the mannequin, the stand, and the measuring equipment, as well as user's manual. From all of us at Team Zippy, thank you for watching, and we look forward to answering any questions that you might have.